Hi, everybody. My name is Landon. Thanks for taking the time out of your schedule to come to our talk. As you can see, it's about Spark streaming, and we'd like to walk you through some of the headaches and, in turn, breakthroughs that we've had in our years of building continuous applications on Spark streaming. So again, my name is Landon, and I'm a data engineer.
And I'm Jack Chapa. I work with Landon on our data products team. So today we're going to be talking about Spark streaming. Over the years, we've had many different tools we've used to manage the volume of data we process. And lately, we've found that Spark streaming is a very powerful tool. And we use it to reduce the latency with which we process data, to handle the increasing volume that we've received. And it's a really powerful tool, but there's a lot of complexity to it. And over time, we've learned a few tricks that we found to be very, very, very useful. So we're hoping that today you guys can learn from some of our mistakes and take something away from it. We know that everybody is on a different part of their journey, and we're hoping that everybody is able to take something out of this. So whether you're just starting out or you've been doing it for a little while, we're hoping that there's something for everybody here. We'll start off by talking about some basics of streaming, Spark streaming in general, go over some of the high-level concepts, and then we'll get into testing and monitoring with the ways in which we can keep these applications running stably in production, and then continue to iterate on them. We'll also spend some time talking about different configurations, some tricks that we've learned, a little bit of time on how we manage our Kafka streams within our streaming applications as well.
So our company, SpotX, we're based in Denver, Colorado. Our sort of business purpose is connecting publishers and broadcasters. What that means is we serve most of the world's internet video advertisements. I know it's everybody's kind of like favorite subject matter in the world. But that's one of the revenue models of the internet. So we connect people who want to advertise on the internet in a video format with people who want to monetize their content. So you think of Spotify playing you a video ad. We don't create video advertisements. We are the technology that makes that sub-second. And we, of course, as we're serving hundreds of millions of records a minute, millions of auctions a day for all these different large companies, we naturally generate a lot of data. Here's kind of a general overview of what our data warehousing platform looks like. As you can see, a lot of open source tools up there. We use some tried and true ones like Hadoop and Spark. We build a lot of stuff in Scala with some Python here and there. And we do a lot of our high message throughput with Kafka. And recently, we've been building a lot of Druid in production for our real-time aggregate reporting. There's a lot of statistics up there, but in general, the takeaway is we do unreplicated about 20 terabytes, unreplicated and uncompressed a day on an average day. That tends to spike as people are ending their campaigns in a season for ad revenue and whatnot, their campaign spends. We do, on average, about 100 million records a minute. That's across a bunch of different business sectors, but it's kind of an average number to show you what we're doing and why Spark streaming would be applicable. We have data science teams and analysts around the company that are running their own daily Spark apps, some MapReduce, mostly Spark, user queries in Hive. But since today's focus is on those streaming apps, I want to touch on why it's so critical for us. So like we've touched on, we have a lot of data. We could batch process it, as a lot of companies have done before us, but Spark streaming is the best way for us to continuously process all of this information, react to it, store it in our data warehouse for querying by our analysts, our reports, our data scientists for ETL, your typical processing. You can do some of this machine learning on those quick streams. And most importantly, we like to react to live situations that are happening in our marketplace. So Spark streaming allows us to, gives us the opportunity to react logically in those situations. And then metadata processing and visualization of all that's happening around our marketplaces and our networks allows us to visualize. We physically put these on monitors all around our pods so that we can see when something may be spiking or something seems to be flaring up. So Spark streaming is critical to this entire infrastructure. Because everybody here might be in a different point in their roadmap or their journey with Spark Streaming, some of you maybe have done this for twice as long as we have. If so, come talk to us and give us your tips, because we're still learning too. But some of you may be just starting out, and you came to this talk hoping to mitigate some of the risks or headaches that we've been through, and we can provide you with some of the breakthroughs as well. So just to get us all on the same page, quick overview of Spark Streaming basics. Spark Streaming is an extension of the core API. It allows you to process streams of data in a micro-batch architecture. The structured streaming has kind of expanded beyond this, but this is the traditional implementation. You can read live streams of data and process them in self-contained jobs at regular intervals. So you might want to connect to a stream and process it every 30 seconds, applying some business logic, some ETL, writing it to a data warehouse, something like that. When you read a stream, you can use all sorts of different products. We use Kafka, so topic is an interchangeable term in this case. So you might hear stream, you might hear topic, same thing, stream of data. A dstream is what happens when you query or you consume that data inside of Spark. It creates a sequence of RDDs that you can apply arbitrary logic to in the same way you can RDD or a data frame or a data set. And again, a batch is just assigned by the batch interval you choose. So if you choose 5 seconds, 45 seconds, 5 minutes, that is the time in which you will consume data up front, apply your general logic, and then start the next batch. So that's Spark Streaming at a high level.
Great. So one thing we found when we first started building these applications is there were we saw a lot of anti-patterns start to emerge. We saw a lot of testing in production. We saw a lot of, this is distributed, this is hard, so we have to just throw it in the prod and see if it works. And we kind of threw away a lot of all the work we'd done around building our applications. So what we'd like to spend a few minutes talking about is how you can quickly set up testing for these types of applications and test them in the same way you would test other applications. One thing right off the bat is that you absolutely can test Spark in local mode, and this is quite obvious probably to many, but it's something that you can do to get up and running really quickly. So you can run Spark in these applications in a Docker container. You can set up unit tests for them. You can test them in much of the same way as you would test the traditional application. You might need to set up specific situations for dealing with like a high load test or simulating production. But to test the basic functionality of your applications, you can run them locally. And the biggest change you're making is simply initiating your Spark context in local mode. With either a dynamic number of workers or you can specify a number as well. One thing that kind of came up for us when we were first debugging these apps is we would have some issues with when they're being built. When you were attempting to run a debugger, sometimes the jars wouldn't be available, or we would have some various problems. One thing you can do is if you're just trying to run a debugger in your local environment, you can just change your, this is in an SBT sort of context, change those to compiled, and it'll build those in. Alternatively, if you're in a unit testing context, you don't have to worry about it since you'll be operating out of your test directory.
Right, so if you run into a scenario where you have myapp.scala in your source main folder, and you hit run, you're like, cool, I'm going to run my Spark app on my machine. This is so great. And then it immediately says, where's Spark? I don't know what Spark is. So you have two options at your disposal. You can either clone that code into your testing environment, and then anything that is considered provided will be symlinked at runtime, so you can just run it out of test. Or if you don't want to clone it and you just want to keep it in main, then you can temporarily flip the dependency to compiled. I prefer the former, but both can kind of get you there. So that allows you to run the same application you would run in production inside your local environment, obviously without the scale. So like you said, great for business test case logic and things like that.
Totally, yeah. And so just as a quick example here, this is a pretty simple test setup. You're creating a Spark session, and this wouldn't be in a streaming context here, but simply reading in some data and then doing a simple assertion on it. And so this happens to be reading from Cassandra, but this sort of demonstrates how you can create a pretty simple easy unit test using Spark in your local environment. Another thing you can do with streaming apps in particular is set up pretty effective unit tests. So within the Spark Streaming API, you can use a queueStream method, which is used to sort of stage and set up some predefined batches that you want to test against. There are some other things you have to do to get that working, such as clock management, and it can be pretty tricky to keep, especially since as versions of Spark iterate, there's going to be some changes to the API. We like to use a number of open source libraries. Spark Testing Base is one that we've found very useful, and the other ones on here as well. And these are valuable if you want to test any sort of like a dstream workflow. So maybe you're running operations on them, or you have business logic you want to assert. The big picture is you don't have to throw away unit testing and good design principles just because you're operating in a streaming environment. So this is an example library, the Spark Testing Base. We found it useful since it sort of abstracts out a lot of the streaming concepts. So you're effectively just making these lists to define your input and your output, and then you can call into the methods within your application to validate that they're performing correctly. This is a pretty basic example, but what's happening here is we're asserting that whatever this application is doing is correctly mapping some data stream into a case class. There's a lot of convenience methods in here that you can use as well. Since you have access to this mock Spark session, you can parallelize and make RDDs and do other functions you might need to do. One note, as you do, pretty much any of these are going to require more memory than like a typical SVD test context will give you. And so definitely you're going to want to give yourself a little bit more overhead there. And all of these libraries have great write-ups on how to do that.
Great. So I'm going to shift the focus to monitoring. So this is kind of a broad topic. But in our view, because we have so many streaming apps in production, we want to keep track of not only how much data is being processed by all of our live marketplaces, we want to know how our applications are doing processing them. So 99% of the time, things are going great. Everything's chugging along. We'd like to see, over a series of time, are we seeing regular spikes during the day of message throughput from a particular topic? Are we seeing slowdown because of a resource allocation problem or an availability problem? Is somebody from our data science team using 4,500 cores in one queue and destroying one of our applications? No diss to data scientists. It's just a made-up example. Didn't happen to us. But it's really important to us, and it's a topic I'm very passionate about at our company. So I'm going to talk very briefly about how we track and visualize performance of our applications. So at a high level, monitoring is really great because you can see over a long period of time, or even short time, how your apps are performing. You can see individual steps in your streaming jobs, what could be causing inflation, like how are the different pieces running, where can you optimize. But more importantly, it can show, if you look at the spike on screen there, those are from the same event that we had with the streaming app, where both the overall batch processing time, so all of the logic that gets executed, spiked big time. I think this is an app that runs normally 14 seconds a batch, and it spiked up to almost a minute. And then you can see in the top graph where one of the tasks exploded from being normally milliseconds to being like 3 seconds. So that does not scale. So it does a great job of exposing problems and bugs. If you haven't seen this before, this is Grafana. It's a really, really great tool. Highly recommend it for visualizing and monitoring your data. And underneath it, the database is InfluxDB. Really great time series database for plotting points over time. Very high throughput, very stable. We really, really recommend that combination. So again, the opportunities to observe your app in a visual sense and digest what it's doing versus having to dig through logs or report those to some alarming app, it's a really great digestible way to consume that information. And if you do like us, we take monitors, they're not nearly that size, maybe a little smaller, and we put those up in our pods, and we just cycle through these Grafana graphs. So when we get up to get a coffee, we might say, hey, does that spike look weird to anybody else? Oh, that's on that particular topic. We should go ask our marketplace if they're testing something in production on accident, because they just spiked a bunch of data. So this is all beautiful, but monitoring can be really tough. And in Spark streaming apps where you have a high message throughput, it can be a real challenge. So up here is a slide I'm particularly happy with. This is some example code that we had in production a few years ago that was calculating these 3 metrics. So we're counting the records in a batch, we're tracking our offsets from Kafka for that batch, and processing, or calculating our processing and time delays. If you've built a streaming app before, you likely see this information when you go to the streaming tab of your application master. You'll see on there all the batches that are in process, all the batches that are in waiting, as well as that level of information. So Spark has all that information, but inside of your main method in your Spark context, it's not exactly easy to have that, to get access to that information, at least at first glance. So a less than ideal approach to doing this is to make the app calculate all of this, or to dig it all out yourself manually. So you can take that dstream and do a .count method on it. But for dstreams that are maybe imbalanced at a partition level, that count can be very inefficient. It can take a long time. It might not even finish. You might on some of your boxes. So not scalable. Might work for smaller stuff, did not scale for us. Tracking Kafka offsets. That's an example of a Avro generic record coming from Kafka. So it has at the top of the object the topic, offset, and partition information. But it's a 4HRDD and a map. Seems kind of a little much, right, to have to do all that just to access what we're accessing, right? It's like we should just know that. Spark knows it. And then you can also kind of ham your way into calculating your own processing time and delays around each step in your pipeline. But because Spark generates action plans around the transformations and actions you choose to do, it can be difficult to really understand where the inflation is happening. So this is where something called listeners comes really handy. It's built into the developer API. Not a lot of people know about it. I've only talked to one person on the internet that has actually used it. And so we've done a lot of work with them in our streaming apps, and they are, across the board, our solution for monitoring. The kind of holy grail of all this is that the performance metrics on screen here are all calculated by Spark in the background by the Spark listener bus. So I'll let you kind of soak in that slide. There's not a lot of code, but that's just a lot of methods. But what you're looking at is that package at the top of the screen. There's a trait called the streaming listener. So this is my favorite thing in the last year or two with working with Spark. I love this package. There are those 8 convenience methods. So you see for different events that are common in a streaming app. You have on receiver started, stopped, and errored. That's when a executor is receiving data from Kafka. So you can take action on any of these events. And then there's my other favorites, which is the batch submitted, started, and completed. So if you wanted to take action every time a batch completes, you can do that here. You just implement your logic by overriding that method. Same thing for doing output operations. If you start a write to HDFS or a database, or when it completes, take action. Again, if you look inside those methods, there is an argument for each of those. They're very verbosely named, but if you look at on batch completed, that is a beautiful little object that has all the information we've described on the previous slides. It's prepackaged for you. It's got offset ranges. It's got partition information. It's got topic counts. It's got batch performance statistics. So the batch just completed, and this little present is waiting for you with all the information you need to offload to your reporting database. We're not going to spend too much time talking about it because we have an in-depth talk today at 5:30 with our coworker Ben Story at room 3016. If you're interested in this, I highly recommend it. I think it's very valuable information. It's a deep dive into how to implement this yourself, and we'll also be giving out the code that we use at SpotX to automatically offload your Kafka offsets to MySQL and write all your performance metrics to Influx and Grafana. So you can take it. It's a one-liner in your streaming app, and you're done. We're really happy with it, so I hope you'll come and check it out. A note on that Kafka offset recovery information. So again, Kafka offsets are just a mathematical representation of where you are in a stream. So when a stream starts and it's it's firstborn, you have a Kafka offset of 0. And then every message independent row that comes after that, is 1, 2, 3, all the way up to 796,852. So we keep track of those numbers for every topic and partition within that topic so that every time we complete a batch, we offload those offsets, we manually manage them, so that one, if our app dies, we can just pick up exactly where we left off, or we can replay if we want to. So there are lots of offset management solutions baked into Kafka, baked into Zookeeper, baked into other solutions. I think Confluent has some great stuff for it. We find that manually managing is good for our business model because we like to replay sometimes. So we have tools where we can just change the offsets and say, cool, let's start back, let's rewind and replay this, which can address a lot of issues if there's some kind of garbage data coming through in production. It doesn't happen very often, but we love having the security blanket and the flexibility. Again, all this code will be up there. We'll release the slides later today, and we're going to have this up on our GitHub. So don't worry too much about it. But here's how you can write the offsets to MySQL with that convenience object. You have that topic object. You can loop through that offset range, form a SQL statement, and write it to your database. And then when you want to read them, if you haven't subscribed to a Spark stream before, or excuse me, any stream using a Spark context, you just have to pull those offsets via a query, so pulling them from state, form a strategy, and assign them to your stream. So this is some example code of how we do it in some of our libraries before. But quick breeze through this code can be a bit much. I'll let you take it in. But we do a select statement against that MySQL database, and we turn it into a map that has a topic partition and a long. That long is representative of that big number, so this is the last row that I processed. So we just do some stuff to kind of prettify it, put it in that map, go back to where we subscribe, and you generate a strategy. And this is all you have to do to tell your topic, or tell your app where to pick up within the topic. So you can see there are two consumer strategies. Those are Kafka libraries. You can choose subscribe, which is our fallback if we can't fetch our offsets, or if we fetch 0 offsets. It says, give me the latest stuff on the stream. I'll worry about it later. So don't do nothing. Just start with the fresh stuff. But if we do get our offsets, use the assign method and pass that offset map that you built inside. And then when your stream starts, it'll start exactly where you last left off.
Great. So in addition to tracking those sort of batch level metrics, sometimes we need to keep an eye on how intra-batch metrics are doing. And a lot of times when there's a problem in production, and we mentioned it briefly earlier, sometimes it's not a problem with your Spark app. There's some external dependency. Maybe you're persisting the data somewhere. Maybe you have some high, maybe like some high latency with some other external process. And what can happen is if you create good timing blocks around some of these actions, it can really help. And this is a slide we showed before. In this case here, we are wrapping a SQL operation that was being performed in action. And by wrapping that, we were able to quickly track down what happened. And what this does is it lets you react well. It lets you escalate your alarms to the appropriate teams. If you're in an operational situation, you don't want to wake up the developer if a different person can fix it. I mean, at least we don't want the developer to be woken up. And then that allows you to appropriately react to the problems and quickly resolve the problems. Because if you don't have these detailed metrics, it might take you a little bit of time to figure out how to fix the problem.
And in addition to that, you don't have to tail any logs.
Yeah.
Which is great.
Yeah.
If it's 3 in the morning and you have to wake up to fix this, you just open up your graph and you say, oh, the MySQL write took a long time. Seems like MySQL's having an issue.
Yep.
So.
And we aggregate failure, like either SQL write failures or other type of operations that might fail to make that alarmable as well. Other tools we use for monitoring our heartbeats just to make sure the app's still running. You have to be careful of heartbeats though, because they don't always take into account like queuing delays and things like that. So if your data's, your app might be processing data, but it might be so far behind that it's maybe not useful, or at least it still represents a problem. We also schedule monitoring jobs for our streaming applications. These handle things like versioning, updates. We don't like to manually run applications in production. We like to let our tools do that for us. And so in combination with our continuous integration pipelines, we'll make sure that not only are the apps running, are they their correct version, and if there is any failures that can be detected or restarted or recovered from, we can act on those as well. Yeah, so those are sort of the big things there. And one thing that comes up too is, if just because something doesn't have an alarm doesn't mean it's not valuable information. So it's important to periodically audit how your apps are running. Are they, over the last month, are they performing worse than they were before? Are there things we can do to improve that? Are we going to need to adjust resources? Having this information is very valuable.
So I'll talk just for a moment about batch intervals. So again, that is the assigned time you want to process a chunk of data with some logic. So if you want to do it every 30 seconds, that means you will consume data, apply your logic or your transformations, finish, and start again, and repeat. A lot of times when people are first starting out, they can struggle with what's a good batch interval I should set, how much resources should I allocate, and it's a fine little dance. But there is a good way, if you ask yourself the right questions, to optimize for both the speed and efficiency of your app, as well as being an efficient steward of the resources you're allocated. And this can apply to people who have both on-premise clusters, like a Hadoop cluster that's running Spark, or something like Azure Databricks. So if you have like cloud spend. Again, an appropriate batch interval is important if you want to have an app that is efficient in terms of processing the data in a timely fashion and using your resources appropriately. Its effectiveness is affected by how much resources you give it and what type, as well as the quantity of the work you're applying. So what actions are you doing on the data that you're ingesting? And of course, how much you're actually ingesting. And to some degree, the quality of the data you're ingesting too, if it's like small and consistent, not with like a lot of like deep nested structures, then that makes a difference too. So the golden rule is that you want your processing time for each batch to be faster than the interval that you set. So that would be 25-second processing time for a 30-second interval on a regular day, but not so fast that resources are just chewing through it and then sitting idly for the rest of the time. I hope that makes sense. Because if they're just sitting there, then they're held for an infinite amount of time while the app runs, and they could be used elsewhere, meaning you've over-allocated. So here's some questions you can ask yourself to set a good batch interval from the start or give you a good thinking place to go to. How quickly do you really need to process data? Like streaming is a very hot topic. It's in a very attractive application to a lot of to management. But if you actually don't have a use case for having it very quickly, then you don't have to do it every 3 seconds. Maybe you do every 5 minutes. Streaming is really built for not several minutes at a time. It's really built for seconds and minutes, not like multiple minutes. Otherwise, you have a batch application, right? But think about it and see, can you slow it down? Can you have a less hungry or a resource-hungry application? It depends on your budget allocation. Do you have like a maximum spend if you're in the cloud? Do you have a throttled queue if you're in like an on-prem with a fair share scheduler? So think about it. Can you increase? Can you cut back? Like, what does your workload look like? For us, we have very high message throughput, so it's very tempting to just throw CPU and memory at it. But we find that a lot of times we've over-allocated a lot of our streaming apps, even though they're doing a lot of work, just because of how efficient Spark Streaming can be. So when in doubt, think about both your resource allocation and your batch interval, because the size of your interval gives you more time to process your information. So if you're having trouble keeping up, you're like, oh, I'll just increase the batch window and give myself time to process the data. But you're also consuming more data because you've opened your window up for every window. Smaller interval, it's the opposite. Here's some tips. Finding a good one. I highly recommend starting small. Choose a small batch interval. Go with a few seconds. One's maybe a little optimistic, but it's doable, especially if you're not doing a lot of heavy work. Maybe 5, 10, 15 seconds, 30 seconds. See how that feels. And then go with modest resources. Do a few dozen executors, 2 to 4 cores, a modest amount of RAM for each one. Understand, it'll be pretty quickly, you'll know pretty quickly if you don't have enough RAM, right? We know what an ohm looks like. So you can bump that up and you can change those to match. So whichever you have more supply of, so if you have more flexibility on time, like you don't need it to be processed so rapidly, then increase the time. But if you have all the world's resources to throw at it, then do that. And if so, please come share it with us. We could really use some more. Again, processing time being less than your interval is great, but comfortably so, not significantly so. You don't want to waste resources. A few kind of final notes on resource allocation. Again, scale down when you can. If you're sharing a cluster with other users, this frees up resources that for other users to use more appropriately, and the closer you are to a full cluster utilization that is appropriate, the more bang you're getting for your buck. And then the same applies for dynamic cloud spin up. You're spending money for every cycle you're using. So be thoughtful of that. You might win some brownie points with management. Preemption. Not a lot of people know what this is. This is a function of shared scheduling where higher priority applications and queues can take resources from lower priority queues when they need to. So if you have stuff that has to meet SLA, stuff that's important to the business, it can yank out resources from other apps that says, you're not as important as me, I need this. If your streaming app is important, then you can avoid this by putting it in its own queue with prioritization and optionally disable preemption from that queue and say, sorry, you can't steal from me. And then for your Kafka topics or a Kafka equivalent, set an appropriate number of partitions so that you're achieving parallelism that's appropriate for the volume of your data. The higher the volume of data you're pushing through a Kafka topic, the higher partition count, generally speaking, you'll benefit from. So if you are having a high throughput of data into a Kafka topic, and you're noticing that Spark is really slow on the read and it's not parallelizing appropriately, it might not be that you're inappropriately allocating Spark CPU cores. It could just be that it's hitting the maximum number of partitions that Kafka has for that topic, and it says, I can't feed you any more data. So if you flesh that out and kind of and parallelize it on the Kafka side, then you can benefit from the Spark side as well. So in a very general sense, it doesn't apply across the board, but generally speaking, the higher your partition count, the greater obvious parallelization you have. Quick shout out to just some helpful configuration settings that we have. I don't need to bullet through all of them, but Spark will dynamically allocate memory in your heap to both storage and execution. Storage is for caching and persisting of data sets, data frames, RDDs. And the other is for execution memory. That's everything else that's operating on your application and holding it in memory. That's not the same as caching and storing. We found that in streaming apps, most of the time we don't do caching and persisting. We just take one and we slowly transform it into different things over time, and we pass it along. So you can set the storage memory, you can throttle that down if you think Spark is not correctly or most efficiently setting that fraction for you. Deploy mode cluster, put your driver out on a random worker node instead of the edge node. That's great for decoupling from edge hardware. Cryo serializer, definitely do that instead of the Java serializer. It's faster, more efficient. RDD compression, not necessarily applicable for everybody, but we like it for some of our higher throughput apps. So Snappy is great for network transfers. Shuffle service enabled. There's an external shuffle service between like Spark and Yarn that you can enable. It requires some extra other settings to enable, but definitely give it a look and see if it's for you. If you have a very shuffle-heavy app, like for joining, that can really help out a lot. And then the block interval. That is the number in milliseconds that a Spark streaming batch will wait, listen for data from a stream as it creates partitions. So you can have, it's kind of a tuning knob for parallelism on the Spark side. So if you don't have a lot of flexibility on adjusting your Kafka topics because you have a systems person who doesn't like you, then that's at least something you can do kind of in the meanwhile and hopefully squeak by. And Kafka. So if you're going to be committing and managing your own offsets, turn that to false so that Kafka doesn't know, like you're not sending back to Kafka what offsets you processed if you're going to be manually managing them. One last configuration called backpressure. This is really great if you have irregular spikes in throughput on your streams. We love this because we have, events that happen where all of a sudden lots of people are watching ads all the time. The holidays are a big one for us. And so we see lots of data, way too much data. And it's like, okay, well, our apps could probably handle it, but backpressure is a really great way to set a maximum per partition in a Kafka topic. And allows you to say, okay, it's essentially a filter, right? So you can say, okay, I'm gonna stay up, I'm gonna process you, but I'm gonna kind of ride this wave out. Two benefits at startup, keeps your app from being overloaded in that first batch and then immediately falling behind, and during peak load. So it can kind of ride out those big waves. So those are the settings you can use. Enable backpressure, max rate per partition. There's not as much documentation on this, so this is important, but that is the maximum rate in messages per second per partition when reading that topic. So keep that in mind. There's also a rate estimator that we love. It's PID-based, and that you can tune it a little bit, but it will effectively read the performance metrics of every batch at the end and slowly tweak the acceptable throughput based on your app's performance. So is it saying, I'm constantly falling behind, I need to pull it back a little bit, or I'm chewing through this data like a really crazy app, and I can afford to take on more, and it'll dynamically alter that. So if you can afford that, and you don't need everything all at once, that's a really great estimator for that. There's a great blog post by a Databricks employee on LinkedIn that you should definitely check out.
Cool. And we want to leave some time for questions, so I'll quickly go through these. We have a few operations transformations that we run on these streams that we found valuable. These are all in the documentation, and we wanted to highlight them though. Transform that gives you RDD level access to your D stream, so helpful if you're enriching it with joined data, maybe with another RDD. Update state by key, map with state. Super useful. They apply a function to each key, so it's really helpful if you're trying to keep track of state between batches. So an example might be a rolling join between two streams where you have a high join overlap, and then you await future batches for the remainder of the data. Super helpful if you're trying to bring multiple data sources together. There's other uses as well. And then reduce by key, which we use for a variety of reasons. Deduping is one of them within a batch. So if you have a key that's coming in, you can use that reduce by key to dedupe those into a single record. Alternatively, you can do any other type of aggregation with it that you might want to do. So here's an example. We have an article on this on our blog, but there's if you were to try to join some static data onto a streaming data set, you would basically load up your D stream and your RDD. They both would be keyed using the same value, and then you would just call transform on it, and then apply your join within the context of that, because now you're referencing it as an RDD.
Really great for like enriching data as your streaming updates come in.
Yeah, definitely. It could be useful too if you maybe apply some updates to this data as well, if you need to get more values for it. And so just to summarize on that, as you're joining this data, if you're bringing in data that you have to join, there's different ways you can handle it. If it's sort of static or fixed data, you can broadcast it out. That's not going to be changeable though. So if you have to reload it per batch, that's not going to work so well. So you can also just read it back onto the driver or on the worker every batch, and then perform any joins you need. If you need any sort of a connection pool, you can have each worker manage its own pool, which works really well. So to review, we've gone over a few topics, and hopefully these are valuable to you. Feel free to come find us afterwards, and we'll be happy to chat more about any of these topics. Here's our contact information. Feel free to reach out if you want to follow up on anything.
Yeah.
Yeah.
That way they can write it down.
Yeah, good call.
Yeah. What do you mean? Yeah. Yeah, I'd be happy to talk about that offline. Structured streaming isn't, for our use case, quite as fully fledged for some of the features we use that are in the previous APIs. We use kind of like 2.1 to 2.3 right now, some 2.4. But as more features go to structured streaming, we're slowly migrating. But you're right, it's definitely much simpler. Yeah. Thank you.
Thanks.
Good. can ask your question.
Yeah, we can talk.
Thank you.